So chapter 15 in the Klein textbook is split into two different topics. The first topic is all about IR spectroscopy, and the second part is mass spectrometry. We've already done a lot of IR in lab, so instead of spending lecture time on it, I made a supplemental video where if you feel a little rusty, you can go back and watch that on your own time. But the most important thing with IR is knowing how to quickly decipher what peaks you need to interpret. The big thing, too, a few people have asked me about is what they need to know. Specifically, do they need to memorize peaks? Well, that didn't transfer very well. There we go. I will give you this chart on the exam so you don't have to memorize where all the peaks are. However, if you can get to the point where you don't need this chart, more power to you. And third term, you will no longer have access to this chart, so the quicker you get used to deciphering IR data, the easier your life will be next term. Sound good? All right. Let's take a look at mass spec. Mass spec is a really, really powerful tool that organic chemists and chemists outside of organic chemistry use on a regular basis. And I'll show you guys the kind of cartoony version of how it works. Let's say you've got a generic compound with a carbon-carbon bond. We know that covalent bonds have shared electrons, so I'll draw those as two red electrons in between each of these carbons. What we're going to do is we're going to smack this with an electron beam. And when you hit this with a bunch of electrons, it's kind of like playing billiards. Some electrons will come in and actually dislodge other electrons that are in covalent bonds. And when this happens, you'll form a complex. And just for the sake of argument, I'll show one electron being knocked out of the interior carbon-carbon bond. So we do this, we dislodge an electron, so I'll show that as plus E minus. This compound right here, what charge should it have? Positive, right? Because we kicked off one of its electrons, so technically it's a cation. In addition, it's got an unpaired electron in there, so people will call this your radical cation. Ultimately, these radical cations are highly, highly unstable. They tend to fall apart into fragments. And during this fragmentation step, this electron will hop over to one side or the other. And so, for example, the carbon on the left-hand side won't have an electron, meaning it's a cation. And the carbon on the right gets the electron, so it will be the radical. So the radical cation splits into two pieces. The interesting thing with mass spectrometry is you can only see charged species. You can't see uncharged species. They're invisible. So mass spec can see this radical cation and this cation piece, but it can't see the radical itself. Radicals look like they should carry a charge, but we know they don't. When you actually go through and do the formal charge is neutral for radicals for the most part. So then the question is, well, why does mass spec only work with charged species? And I'll show you guys, again, the kind of cartoony view of the physics here. And let's say you're a cation, and we're shooting you down this way. What you can do is actually introduce a magnetic field. And so this magnetic field, for example, will have a north pole and a south pole. Typically, these are electromagnets. If you're that cation entering this magnetic field, what do you think will happen? It's going to be attracted to the negative side, right? So it's going to deflect downwards. And so it'll start to go in, and what I'll do is I'll draw this dashed line, and then we'll actually show the deflection. So we know when it goes in, it's going to start deflecting down a little bit. And then ultimately what it's going to do is it's going to hit a detector back here. And what the mass spec does is it essentially measures this distance of deflection. That's really important for mass spec. What do you think can impact that distance of deflection? Anybody have any ideas? Yeah, whether or not it has 2 positive charges or just 1, absolutely. What's another big thing that can impact it? The size of it, how heavy it is, right? A really light molecule is easier to deflect than a really heavy molecule. So it's essentially used to study the charge to mass ratio. The other thing that can be used to change the deflection is the strength of the magnetic field. However, that's normally just held constant during these experiments unless you're doing really advanced mass spec. So what we're really interested in is this charge to mass ratio. Normally when we're doing mass spec, we have a charge of +1. So really the charge to mass ratio is just going to be your mass, right? But that's really important. As a chemist, we oftentimes want to know how heavy an organic molecule is, especially if we don't know what it is to begin with. So again, we'll take a look at this instrumentation. You don't have to draw this down unless you really want to. What you do is you insert your sample at the very edge of the instrument. There's a heater in there that heats it up and vaporizes it. And then basically, there's some components that will accelerate it through an ion beam. That will dislodge some of your electrons, and then, like I said, that goes through a magnetic field, and what we're looking at is the distance that that cation or anion is deflected. For the most part, in the Klein textbook, we're looking at cations. There are mass spec techniques for anions as well, but he just tends to focus on cations in his book. All right, so let's take a look at what a spectrum looks like. So here's an example of a really, really simple one for methane. And if you notice, there's a bunch of different peaks in here. So then the question is, why? Does anybody have an idea for why there's different peaks? What's that? Strength of the bond, right? So potentially what we're doing is knocking off one of the hydrogens, and that would make it 1 unit lighter. So that could be it. So maybe it's fragmentation. Does anybody have another idea for why maybe there's a cluster of different peaks outside of fragmentation? I'll give you guys a hint. How do they study how old dinosaur bones are? Half-life of what? Of carbon-14 for dinosaurs, right? So carbon, for the most part, is carbon-12, like 99% roughly. However, the remaining 1% are different isotopes of carbon, right? So mass spec can actually see isotopic distribution of various atoms, and that's why we see a little bit of range. Specifically, this peak right above here, you can see that's most likely due to the carbon-13. Carbon-13 is something we can see via mass spec. Carbon-14 is so minimal in our environment, it's really tough to see unless you've got a high-end spectrometer. So you can see fragmentation and you can see isotopes. So mass spec is an incredibly powerful tool. Most people are familiar with it from shows like CSI, right? If you watch CSI, they're like, oh, there's a paint chip. This paint came from a Ford F-150 produced in 2006 from a plant in western Michigan. The reality is it's not that good. It'll tell you the molecular weight, which is incredibly powerful. It doesn't tell you a whole lot beyond that. So chemists use this in addition to a bunch of other tools when they're doing CSI-type forensic investigations. So let's take a look at some of the peaks that we need to pay attention to. And the first peak that we tend to pay attention to is our radical cation peak. So let's make a note of that. And typically this is represented as a plus dot, and that's our radical cation slash parent peak. Like I said on that last page, it's that peak where you just dislodge one electron, but it's before any fragmentation has a chance to take place. So this is a really important peak because it's useful for determining the molecular weight of compounds, right? Because it's before anything's fragmented apart. The easiest way to find the radical cation or parent peak is to look at your spectrum, go all the way to the right, and you'll see a cluster to your right. In this case, this is the only cluster. And you typically want to look for the tallest peak in that rightmost cluster. So you guys see how that one's the tallest? So it's typically the tallest peaks in your rightmost cluster. And if your charge is +1, then this is also your mass. Oops. And like I said before, typically the things we're looking at only have charges of +1, so this is pretty easy and quick for us to determine the molecular weight of our compound, right? So with methane, carbon's got an atomic weight of about 12, hydrogens are about 1, so we would expect it to be about 16, which is exactly where it shows up here. There are other spectrometers that are called high-resolution mass spectrometers, where they actually go out to the tenths or hundredths place, or even higher than that, and that tells you a lot more information. But as far as we're concerned, we're only going out to ones places here. So we're looking at just atomic mass units. All right, so let's take a look at a more complicated one. So this is an example of Npentane, so unbranched pentane. And you can see this is what a spectrum looks like for Npentane. And first thing I always do is I look for my parent peaks. So where do you guys think that's going to be? Yeah, it's got to be all the way over here. So this is our radical cation peak. That essentially tells you the molecular weight of Npentane, right? Sometimes these peaks can be really, really hard to see, especially if you've got a molecule that fragments really easily. It can be exceptionally small and hard to spot. But that's the first thing I always look at. The other thing you should look at outside of this parent ion is something called your base peak. And your base peak is simply the tallest peak in your spectrum. And it's not to be confused with your parent ion peak. And typically, if you look at the scale in your spectrum, you'll see relative abundance on that left-hand side. That's just telling you the relative abundance compared to that base peak, right? So in this case, because it's the tallest peak, it's set to 100, and everything else is set to some fraction of that, right? So if you look at our parent ion, it looks like maybe less than 10% of our base peak. So it's not in high abundance. All right, then the second thing is, why are we seeing all these little clusters? What do you guys think? So for example, I see a relative cluster here, second one here, third one here, and then last one down here. What do you guys think that's all about? Just intuitively. Not impurities. We can assume that this is pure going in.
Fractures?
Yeah, fractures, right? So if we put this molecule in and we're breaking it apart, perhaps this peak is loss of a methyl group. So perhaps we lost a methyl cation. Maybe over here we lost 2 carbons, so loss of a CH2, CH3 cation, or sorry, radical. And then so on and so on. Maybe this is loss of a propyl group. And then last but not least, we could say, well, this has got to be some sort of methyl cation peak, because that's the only remaining carbon. Yep.
So using this technique, you don't really have any control of what bonds are going to break?
You don't have control over which bonds are going to break. The weakest ones tend to be the most likely ones to break. So in that regard, we can predict that our base peak, the tallest one, is going to be the result of the bonds that are easiest to break, right? So if you remember back when we were talking about peroxides, we said oxygen-oxygen single bonds are really easy to break. So in mass spec, we would likely see cleavage of bonds that tend to be weaker than other bonds. That's a good question. We're not going to get super into that, but it tends to follow the same guidelines as carbocation stability, right? So tertiary cations tend to be more abundant in your spectrum. than a secondary cation and more so than a primary cation. In addition, if you've got resonance stabilization, those peaks tend to be quite large as well. All right, so let's take a look at some common tips and tricks. So let's take a look at pentane. We'll compare this to some nitrogen analogs. I'm going to swap out one of those carbons for a nitrogen. And then over here, I'm going to swap out 2 carbons for nitrogens. If we look over here, the molecular weight of pentane should be what? And we can go back and even cheat if we want. What do you guys think for pentane? Yep, if we go over here, we'd say that's 70, 71, 72, right? Which should match your guess on the periodic table, or not guess, your math using the periodic table. So this has a molecular weight of 72. Not too bad. All right, if we do the next one, which has an amine off of it, this has a molecular weight of 73. And if you go to the one on the far right, this has a molecular weight of 74. The trick I'll show you guys is that molecules with an odd number of nitrogens have an odd molecular weight. And an offshoot of that is most other things will be even. And I'll just say MWs for molecular weights. So you can see in pentane we have 0 nitrogens. So this one is even. Over here we've got 1 nitrogen. So this is odd. And then over here we've got 2 nitrogens. So this is even. So you can really quickly spot whether or not a nitrogen whether or not you have a nitrogen containing compound by looking at your parent ion and seeing if it's odd or even. If it's odd, that's a good sign that you've got a nitrogen in there, right? If you've got an even peak, that either means you've got an even number of nitrogens or no nitrogens at all. So that can quickly be a good clue that you can work off of. All right? So let's take a look at some of these other fragmentation patterns. Right now we've only really been looking at the main clusters. What we want to look at next is called our M+1 radical cation peak. Is due to heavy isotopes. All right, so I'll show you guys the most common isotopes we'll run across as organic chemists. Obviously, we'll focus on carbons, since that's what we do. Carbon is abundant at a 98.9% level, so it's obviously the most abundant form of carbon. Carbon-13 is abundant at about 1.1%. And then carbon-14 is really just a trace amount. Like I said, carbon-14 is what they use to date really, really old biological samples. However, it's not really useful for mass spec. Carbon-13, on the other hand, is, so we do need to pay attention to that. If we look at hydrogen isotopes, protons are obviously the most common, and these are present at 99.96%. Deuterium is about 0.01%. Oops, sorry, I should do an H, not a D. And so really it's quite negligible. If we go down and we look at oxygen, we've got 2 isotopes that are the most abundant. Oxygen-16 It's abundant at 99.96%. And oxygen 17 is 0.01%. All right, so clearly when we do mass spec, we'll be able to see carbon-12, we'll be able to see hydrogens, we'll be able to see oxygen 16, no problem. This one right here is so small, it doesn't really matter. So small, it is nearly impossible to see. And this is also the case with deuterium atoms, so I'm just going to circle these and cross them out and just say, don't worry about those. They're so minuscule, we just don't see them. Carbon-13, on the other hand, I'll put an arrow up to carbon-14, does have a sizable amount, right? Carbon-13 is 1.1%. We can actually pick this up. We can see carbon-13. However, it's going to be a really small itty-bitty peak, and it's typically going to be 1 unit heavier than your parent ion peak. All right, so I'll show you guys a cool trick that you can do with this carbon-13. You can actually use it to figure out how many carbons you have in your overall sample. All right, so what we do is we can say the number of carbons in our unknown sample is going to be equal to the intensity of our mass plus 1 peak. That's our radical cation. Divided by the intensity of our parent peak. And I'm just going to bracket this so we can keep track of everything. Times 100, all divided by 1.1, because that's the abundance of carbon-13. All right, so let's take a look at an example problem here. Your parent ion has a mass to charge ratio, so that's also represented as m/z, of 68, and a relative intensity, meaning how tall it is, of 100%. Your mass plus 1 radical cation has a mass to charge ratio of obviously 69 because it's 1 more than our parent, and a relative intensity of 4.3%. All right, how many carbons does this unknown compound have? Who thinks they got it? All right. So we can plug this in. First thing we want to do is divide the intensity of our mass plus 1 peak. So that was our 4.3, whoops, not 4.1, divided by the intensity of our parent ion, which we know is 100. We'll multiply this by 100. And we'll divide this by 1.1. Really quickly, without even a calculator, I can say, all right, these hundreds are going to cancel. It's essentially going to be 4.3 divided by 1.1. Being an organic chemist, I don't care for math much. What is this approximately?
4.3.
About 4, right? So we'll just say about 4. And this is honestly what you do with mass spec. you aren't going to get an exact number out. It's going to often have a decimal, but you can't have a fraction of a carbon, so you're just going to round to the closest carbon, right? It's not a perfect science, but it does a pretty dang good job of telling you how many carbons you have in your system. So this unknown compound has 4 carbons. Yep.
So for a problem like this, the only thing we care about is the percent. We don't care about the other information you give us.
You do care about the relative intensities. That tells you a lot of information. So the relative intensities and then the mass to charge values are what you're looking at. But it's important to remember that the relative intensities are just some arbitrary unit, and the 100% is based off the tallest peak. But sometimes your parent ion isn't going to be 100%. So let's do another example where the parent ion isn't 100% and see what that looks like. All right, so example number 2. We'll say, all right, I'm just going to abbreviate this. Our parent ion is at a mass to charge of 96, and it has a relative intensity of 19.0%. Our mass plus 1 radical cation, where's that going to be at for mass plus charge?
97.
Yeah, 97. It's going to have a relative intensity of 1.5%. All right, how many carbons are in this system? Now we might need a calculator. Give me a thumbs up if you think you got it. All right, so let's do this. First thing we do is look at the relative intensity of our parent peak. We'd say, all right, our mass plus 1 peak. That's 1.5 divided by 19.0 times 100 divided by 1.1 is going to be equal to about how many carbons?
7.
About 7. And some people will say, well, what if there's oxygens and other things in there? This doesn't tell you anything about oxygens. It doesn't tell you anything about non-carbon atoms. It's just simply telling you approximately how many carbon atoms you have in your unknown. The number of nitrogens, we know we can use some clues based on whether or not it's odd or even. And oxygens are even trickier than that because oxygens we don't have an easy clue for. But what we will do next is I'll show you guys kind of the process of elimination I go through when I look at mass spec. So let's use the M plus 1 peak to find a molecular formula. All right, so here's an example spectrum. If we look at this, our goal is to propose some sort of molecular formula that makes sense. What I normally like to do is first identify my parent peak. And where do you guys think that is?
Far right.
On the far right, tallest peak. It's going to be right here. And in fact, this chart just tells you flat out, this is your parent peak. So nice and easy, right? If we look at 87, this has to be our mass plus 1 peak. Before we do any math, though, I always stop and ask myself, do you think there are going to be any nitrogens in here? What do you guys think? So we look at our parent peak and we'd say, all right, it's 86, it's even, so it's got to have an even number of nitrogens if it has any at all. So it's either got to have 0, 2, 4, 6, or so on, but it's really, really unlikely that it has just one nitrogen in there. All right, so we know that. Let's try to determine how many carbons we have and go from there. So I'll give you guys a minute to work on this. All right, give me a thumbs up if you got the number of carbons. All right, perfect. So like I said, the first thing I do is I identify my parent peak, which we said was 86. We said because it is an even number, there's either an even number of nitrogens or no nitrogens at all in the system. So that's the first clue. We know the molecular weight. That's another big clue as well. Now what we need to do is determine the number of carbons. So that's step 2. Oh, here we go. All right, so what we need to do is take the intensity of our M plus 1 peak, which was 1.2%, divide that by the intensity of our parent peak, which in the chart was listed at 20.9%. We multiply that by 100. We divide that by 1.1. And what were you guys getting? About 5. So about 5 carbons. Okay. All right, so now what we've got to do is some problem solving. We know that there's 5 carbons. We know that maybe there's nitrogens, but if there are, there's got to be either 2 or 4 or so on. And we've got to basically deconstruct this and figure out which atoms are in this unknown compound. So how do you guys think we should go about problem solving this? What do you think? Yeah, so how much does 5 carbons weigh? Not everybody all at once. So each carbon is 12, right? So 5 carbons weighs about 60. All right, that means that our parent was 86 minus the 60. This is from the carbon. Means that we have 16 left over. Oh, 26, excuse me. I can't do math. All right, so 26 left over. All right, so let's go back to the nitrogen claim, right? Do you think we have nitrogens in this compound? Do you? How much do nitrogens weigh? 14. We either have 0, 2, 4, 6. Do any of those make sense? No, because if we had 2, that'd be 28 alone. So this alone tells us there's no nitrogens in this compound. So they would weigh more than the leftover mass. All right, so we've got 26 left over. All right, what do you think could be making up that 26? And we're assuming simple organic compounds. So don't go nuts on the periodic table looking at transition metals. Yeah, probably hydrogens. What's another atom that's commonly found in organic compounds? Oxygens, right? So typically this leftover is going to be made up of oxygens and or hydrogens. We know nitrogen can't possibly work in this situation, so we've got to go from there. All right, so we've got 26 left over. Do you think it's going to be all hydrogens? Nope. It'd be physically impossible to have 5 carbons with 26 hydrogens, right? You'd have some crazy Texas carbons in there. All right, so let's put 1 oxygen in and go from there, right? All right, so we'll say, all right, we know our parent is 86. We know we lost 60. This was from our carbon. And now what we're going to do is we're going to try subtracting 1 oxygen. What's the molecular weight of oxygen? 16. All right, that gives us how many left over? 10.
Where did 16 came from?
16 is oxygen. Right, so that's assuming 1 oxygen. Right, so I'll even put a 1 down here. Carbons, we already said that we had 5 carbons. Was that right? All right, so we're ready to go. Do you think we have 2 oxygens by any chance? No, because it weighs 16. Again, that wouldn't make any sense. So the 10 left over, what do you think that likely is going to be? Yeah. So likely hydrogen. All right, that leaves us in a pretty good situation though, right? So now we can say, all right, this molecule is likely C5H10O. All All right, and what you can do is just start guessing and checking wildly and draw as many structures as you can that fits this. However, it gets somewhat challenging, especially with larger molecules. So I'll show you another trick you can do to make your life a little bit easier. So this is step 3. Oh, I don't know why it's doing that. Determine your hydrogen deficiency index. This is also known as your HDI. And the HDI tells you a lot of useful information, and I'm going to leave our molecular formula up there for a second. But you can calculate your HDI, that hydrogen deficiency index, by going through this formula where you take 1/2 times double the number of your carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogens, so that's X. And what this does is it tells you the number of pi bonds plus the number of rings that you have in your system. So it is a pretty useful tool, right? So if you've got 1 pi bond and no rings, you should have an HDI of 1. If you've got 1 ring and no pi bonds, that will also have an HDI of 1. If you've got an HDI of 0, that means you can't have any rings, you can't have any pi bonds. So it's a really useful trick you can use. The tricky thing is, what if you have an HDI of 2? You could have 2 rings, you could have 2 pi bonds, or you could have a ring and a pi bond. So it's any combo of rings and pi bonds. All right, so let's do this with our unknown compound. All right, so we're going to say HDI for our unknown compound is going to be equal to 1/2 2 times the number of carbons, so 2 times 5, plus 2, plus 0 nitrogens, minus 10 hydrogens, minus 0 halogens. And what does that give us? 1. All right. All right, so let's take a look at this, and we'd say, all right, this means we must have a pi bond or a ring system. All right, so that's a pretty useful clue. So what I want you guys to do is to see if you can draw a bunch of different isomers that might fit this. So I'll give you guys a minute or 2 to work on this. But check with your neighbor. We'll see who can come up with the most. All right, let's just quickly go through and jot down 4 possible options that might fit this molecular formula. So we know the molecular formula, like I said, it is, C5H10O. We know it has an HDI of 1. So that's a really useful tool, and all we need to do is throw out a bunch of various options. So for example, maybe we have a ring system that looks like this, right? 5 carbons, 1 oxygen in a ring system. Makes sense. 6-membered rings we know are relatively stable. Maybe it's a big, long chain system, and there's a ketone in there. Carbon-oxygen double bonds are pi bonds, right? So that could work. Maybe it's a 5-carbon chain with an aldehyde coming off of one end. That could work. Maybe it's a different ketone. Maybe the carbon-oxygen double bond's in a different position. Maybe it's an aldehyde that has some amount of branching coming off of it. Whoops. Maybe it's a ketone with some amount of branching off of it. There's a whole bunch of these that you could draw out. Mass spec kind of helps you narrow down the possibilities, but it doesn't give you the right answer right away. Oftentimes we need other forms of spectroscopy to help us along. So for example, how could I determine whether or not I have this one or this one in our organic chemistry lab? What's that? IR, right? So if we did IR spectroscopy, we could say, well, we'd expect this one to show up at about 1700 for that CO double bond. This one would have no CO double bond in that 1700 region, so it should be empty there. Yep.
With our HDI value, would it be possible to have an alkene?
Yeah, you could also have an alkene in there, in which case IR would be especially useful for determining whether or not you have an alkene or a CO double bond. Exactly. So that's kind of the big takeaway from today is this is one tool we have in order to determine structure, but it's not the only tool we use. Oftentimes we use it along with IR or NMR, which we'll learn later. All right, I think that's where we'll stop today. If you do feel at all rusty with IR, remember to watch the supplemental video that I'll post online. The pod that's due tomorrow is just to brush up on IR, and remember to label all of your peaks. If you do want to get those extra credit points, it needs to be 100% definitive. So come up with some sort of plan to prove exactly what you're proposing. So I'll leave it at that.